So, in the last lecture we had talked about the rate of deformation tensor. Okay. Grad V. Okay. If you are at some location x, okay, and you make a small displacement x plus delta x, okay, the fluid velocity at the location x is v at x. The fluid velocity at this nearby location x plus delta x is v at x plus delta x, okay, and grad v is defined such that v at x plus delta x minus v at x, difference between two vectors, is equal to delta x dotted with grad v. Okay. And I told you that this can be decomposed into three parts: symmetric plus antisymmetric part, symmetric part further decomposed into an isotropic and a symmetric traceless. So, it consists of an antisymmetric part plus a symmetric traceless part plus an isotropic part, which is 1/3 divergence of velocity times the identity tensor. Okay. And the antisymmetric part is the difference between, okay, the gradient of velocity minus grad v transpose, okay, and this extensional part is basically equal to the symmetric part grad v plus grad v transpose, okay, minus 1/3 I del dot v, okay, because at 1/3 I del dot v is written separately here as the isotropic part, which means that the trace of E has to be equal to 0. Okay. Okay, that means that the sum of the diagonal elements of E has to be equal to 0. Okay. And we had looked at the physical interpretations of these. Okay. Okay. The antisymmetric part represents solid body rotation, okay, solid body rotation, okay, and this can basically be written as delta x, half omega cross delta x, okay, where delta x is the distance to a point from the axis of rotation. Okay. Therefore, this is solid body rotation with angular velocity equal to 1/2 of the vorticity. Where vorticity omega is equal to the curl of the velocity. Okay. So, that means that this is a solid body rotation with angular velocity equal to 1/2 of the vorticity. Okay. So, that is the antisymmetric part. Symmetric traceless part represented radial expansion or compression. Okay. 1/3 del dot v into I. Note that del dot v is the divergence, so it is a scalar. Okay. So, this is radial expansion or compression. Okay. And the third component was the symmetric traceless part. Okay. So, the symmetric traceless part E, okay, was defined as a tensor that was symmetric and traceless. symmetric, okay, the off diagonal elements are equal, and traceless because Exx plus Eyy plus Ezz is equal to 0. And I showed you that in 2 dimensions this represents a velocity field, okay, in which there is expansion along one direction and compression along the other direction, such that a volume that was initially looking like this, okay, will at later times become something like this. Okay. Expansion along the x axis in this case, compression along the y axis, in such a way that there is no net change in volume, and in such a way that there is no rotation of the axis. Okay. So, this is extensional strain, okay, symmetric traceless part. Earlier we had discussed the stress tensor, okay. Sigma is equal to sigma xx, sigma xy, and I had told you that this tensor has to be symmetric, okay, this tensor has to be symmetric, okay. That means that the off diagonal elements have to be equal, okay. And I can write this as the sum of an isotropic tensor, which is the pressure, okay. I can write this as equal to minus P into I plus a stress tensor, okay, a stress tensor. P is non-zero even in the absence of flow. It is the isotropic pressure, okay, it is the isotropic pressure. It is non-zero even in the absence of flow. This second part is non-zero only when there is flow, okay, and it has to be related to gradients of the velocity field, okay. Note that since sigma, the stress tensor, is symmetric, this also has to be symmetric, okay. So, therefore, tau also has to be symmetric. Now, Newton's law of viscosity, okay, is determined assuming that the relation between the stress and the velocity gradient is a linear relationship, okay. The relationship between the stress and the velocity gradient is a linear relationship, just as the relationship between the mass flux and the concentration gradient is linear with diffusion coefficient d, or the relationship between the heat flux and the temperature gradient is linear. So, in this case the relationship between the shear stress and the velocity gradient is assumed to be linear, okay. The stress is symmetric, okay, and we know that the antisymmetric part of the rate of deformation tensor does not cause any stress because it is solid body rotation, and in solid body rotation there is no deformation of the object, in that is, there is no change in extension or compression of material elements, okay. So, therefore, the stress cannot depend upon the antisymmetric part of the rate of deformation tensor, okay. So, it can only depend upon the symmetric and the symmetric traceless and the isotropic part of the rate of deformation tensor, okay. So, that is Newton's law of viscosity. This depends upon there is an isotropic contribution due to the pressure plus a contribution due to the symmetric traceless part, okay. Coefficient is 2 times the viscosity because when we calculated the symmetric traceless part we had taken half of the velocity gradient plus its transpose, plus you could have an additional contribution, okay, which is isotropic due to radial expansion or compression. So, this is the linear relationship between the stress and the velocity gradient. You cannot write it directly in terms of the velocity gradient because the velocity gradient need not be symmetric, whereas the stress has to be symmetric, Okay. So, it has to consist of these parts. Okay. Now, the Navier-Stokes equations, okay, for the momentum conservation equation is similar in form to the concentration and the temperature equation. Okay, it is written for the momentum density. Okay. Recall that the concentration equation was partial C by partial T plus divergence of V times C is equal to minus divergence of J, okay, plus any sources. Okay. If I write this for the momentum density is the mass density times the velocity. A similar equation would be of the form partial of rho V by partial T plus the divergence of rho V V is equal to the divergence of the stress plus any body force density. Okay. This is the momentum conservation equation for a fluid. Okay. Note that there is a negative sign here in the concentration equation and none for the stress equation. The reason for that is, as I told you, convention is that the mass flux is positive if it is along the inward unit normal, because it adds to the mass of the volume, whereas the momentum flux is considered positive, the stress is considered positive if the force is exerted along the outward unit normal. Okay. So, because of that there is a difference in the sign. Okay. Now, the left and right side of this can be simplified. Okay. So, first the left side, okay, partial rho. And note also that this is a vector equation. Okay. So, there is one equation for the x component of the velocity, one equation for the y component of the velocity, and one equation for the z component of the velocity. There are three components of the force at the end, one for the x component of the force, Fx, Fy and Fz, similarly for del dot sigma. Okay. This can be the first term can be written as partial rho by partial T is equal to V into partial rho by partial T plus rho into partial V by partial T. Okay. Let me write this slightly differently in order to make it similar to what we had over here. Okay. So, this I can write it as the divergence of V times the momentum density. Okay. This red color shows you that the divergence is between this velocity V and the gradient operator. Okay. So, let us look at the second term here. Okay. Del dot okay. The dot product is between the red V and the red gradient. Okay. First, I will take the derivative with respect to the red V. Okay. So, I will write this as V and okay, differentiating using chain rule. Okay. Okay. And the second term will be rho into V dot grad and then this V here. Okay. So, first I am taking with respect to rho V the derivative and taking V outside. Second term I take rho V dot grad V. Okay. So, these are the two terms, okay, in this equation when I differentiate by chain rule. Okay. And when I add these two together, I will get, okay, rho into partial V by partial T plus V dot grad V, okay, that is these two terms here, okay, plus V into partial rho by partial t plus del dot dot rho v. And this entire term here is 0 from mass conservation equation. Okay, this entire term here is 0 from mass conservation equation. You recall that the mass conservation equation is partial rho by partial t plus divergence of rho times v is equal to 0. Okay. So, therefore, the entire left side can be expressed as rho rho into partial v by partial t plus v dot grad v. So, let us look at this term del dot sigma here. Okay. Okay, is equal to the divergence of mu into E 2 mu E plus mu B into divergence of velocity times the identity tensor. Okay, so, let us examine that. Okay. Recall that E is equal to half grad V plus grad V transpose minus 1 by 3 I into the divergence of the velocity. Yeah. So, when I take the divergence of this, divergence of E is equal to, I can take the half outside, I will get the divergence, okay, the divergence acting on grad V plus grad V transpose. Minus the divergence of I into del dot V. Okay. In this first term, divergence of grad V, the dot product is between the two gradient operators. Okay. The dot product is between the two gradient operators. So, this becomes half of del square or dot acting on V. Okay. The dot product is between the two divergence operators. Okay. So, this can effectively be written as the Laplacian. Okay. This is effectively the Laplacian. Okay. The second term, I take the transpose, okay, divergence acting on the transpose of the velocity. That means that the divergence operator is acting on the velocity vector, not on the gradient vector. The dot product is between the gradient here and the velocity. Okay. So, the dot product is between this gradient and this velocity, because it is acting on the transpose. Okay. The rows and columns interchanged. Okay. So, this becomes del dot gradient of del dot V. Okay. I should write this as minus 1/3. Okay. So, minus 1/3, okay, the divergence acting on I del dot V. Okay. Divergence acting on the identity tensor. Okay. Identity tensor is basically Ex, Ex, Ey, Ey, Ez, Ez. When you dot it with that, you will just get this as minus 1/3 the gradient of del dot V. Okay. okay, because the divergence is acting on the identity tensor, okay, partial by partial x of Ex Ex. Okay. So, therefore, you just get 1/3 del dot V. Okay. So, this becomes half del square V, okay, plus half grad of divergence of velocity minus 1/3 grad of divergence of velocity. Okay. So, therefore, del dot sigma will be equal to 2 mu times the divergence of E, that is mu del square V plus, okay, half minus 1/3 multiplied by 2. Okay. So, this will be equal to minus 1/3 grad of del dot V. Okay. So, I have to multiply by 2. So, I will get 1 here and 2/3 here. Okay. So, if I multiply by 2, I will get 1 here and 2/3 here. Okay. Plus you have this additional term here. Okay. So, this is divergence of the identity tensor times del dot V, and that basically becomes plus mu B, okay, into the gradient of del dot V. Okay. So, that is the divergence of the stress tensor. Okay. For the particular case for an incompressible fluid, okay, del dot V equal to 0. Okay. In this case, you can easily verify that this term goes away and this term goes away. Okay. Similarly, in the stress tensor, this term will go away and as well as this term will go away. Okay. So, therefore, for an incompressible fluid, E just reduces to mu into grad V plus grad V transpose. Okay. The isotropic, there is no isotropic part because divergence of V equal to 0. Sigma will be equal to, sorry, this is not E, this is E is 1/2. Okay. And divergence of sigma, okay, from this expression here, okay, the divergence of sigma will be equal to mu times del square V. Okay, the divergence of sigma is equal to mu times del square V. So, from this equation, okay, we have simplified the right hand side now, and the equation becomes now rho into partial V by partial T plus V dot grad V. Note that the gradient is the dot product is between V and the gradient, okay, and the free index is the velocity on the right side, is equal to minus the gradient of the pressure, isotropic part, plus mu del square V plus F. Okay. So, this is the Navier-Stokes mass conservation equation. Okay. Yeah. I should note here that the stress tensor sigma had, yeah, this also had a pressure in it, okay, minus P times I, the isotropic part, okay, and when I took the gradient of this, I will get plus grad P, okay. Divergence of P times I will give me grad of P, okay, that is this term. So, this contains a pressure, viscous stress, the divergence of a viscous stress and a body force. Okay. Comparing with the mass conservation equation, partial C by partial T plus grad of Vc is equal to d del square C plus the source. Okay. For an incompressible fluid, you can write this as V dot grad c plus c divergence of the velocity, okay, and this divergence of the velocity is equal to 0. So, it has exactly the same form except that the concentration, which is a scalar, is replaced by the velocity, which is a vector. Okay. So, that is one difference. The concentration, which is a scalar function, is replaced by the velocity, which is a vector. Okay. That is, okay, for an incompressible fluid. Okay. And the only other difference is the gradient of the pressure, something which is not present in concentration and temperature equations. Okay. So, these are the Navier-Stokes equations: mass conservation equation and momentum conservation equation. I will write them again for you. For an incompressible fluid, mass conservation partial rho by partial t plus del dot rho v is equal to 0. Alternatively, d rho by dt plus rho divergence of velocity is equal to 0. And for an incompressible fluid, the density does not change, okay, which means that this implies that the divergence of the velocity is equal to 0. Okay. The Navier-Stokes mass and momentum conservation for an incompressible fluid. Okay. Momentum conservation, rho into partial v by partial t plus v dot grad v is equal to minus grad p plus mu del square v plus the force vector, force density. Okay. So, these are the Navier-Stokes mass and momentum conservation equations. Okay, now that we have derived these equations, these are vector equations. Okay. I will discuss a little bit about a simplification. That is, there is already one simplification here, that the flow is incompressible. I will discuss a second simplification, that the flow is a potential flow, that is inviscid and irrotational. Okay. And after completing those two simplifications, we will then go to analyze transport in an infinite medium for unidirectional transport. Okay. So, I will discuss a little bit more about potential flow in the next lecture, and then I will go on to unidirectional transport. So, I will continue this in the next lecture. I will see you then.